Hey everyone, welcome to the video lectures for section 2.9. So in this section, we're going to be talking about what are called finite difference equations. It's something a little bit different from the differential equations we've been considering so far in this course, but it has similar applications to modeling and things like that, and it also shows some interesting behavior for a very simple first order equation that it takes up to a higher order system to actually get in differential equations. So we're going to start by going through what difference equations are, and sort of how they work. And eventually we'll get to this behavior called basically a chaotic behavior for the solutions that we're going to see a lot later at the very end of the course for differential equations, but we can see it early on for finite difference equations. So let's go ahead and get into what these equations are and more or less how they work. So the idea of wanting to use a finite difference equation to define something is that sometimes for things you're trying to model, a continuous model doesn't make sense and a more discrete or stepwise model does make sense. So what are some situations where this might be the case? Well, say you have a bank account and you're looking at compounding interest. Well, the assumption we make when doing the compounded continuously type of problems that are in the first parts of this chapter, we assume the interest is compounded continuously every day, more or less, or every second. But really, it's compounded monthly or quarterly or something like that. There's a discrete time when money is added to your account as opposed to it being a continuous process. Another case where this might be where a discrete model might make more sense is if you have a species that reproduces, but it reproduces in definite time intervals. So basically, like every 20 minutes, your bacteria divides and you get more. So you could model that continuously, but it might make more sense to look at that in its discrete steps, where basically every time, every 20 minutes, you get a set amount more because things divide. So these and other sort of problems make us think about considering finite difference equations, where basically instead of doing a derivative, you're just looking at a difference from one step to the next. So these finite difference equations basically take the form of yn plus 1 equals some function of n and yn. So basically, I can determine where I'm going to be at the next step, knowing what step I'm at right now, and my value at the current step. What you should think of here is this is something like dy dt equals f t and y. Those are more or less the same thing because in this case, instead of having continuous time where time can be anything, you have n is your time. Your n is your integers that you're stepping up one by one to get from one step to the next. So as before, we consider such an equation linear if it's linear in the y term, and it's nonlinear otherwise. Same as we would for normal ODEs, we call them linear and nonlinear. Now in this case, because we're dealing with y1, y2, y3 through yn instead of a function, our solutions look a little bit different. So in this case, a solution is a sequence of numbers that satisfies the equation. Is a sequence y0, y1, up to yn and so on, so that it satisfies the equation. How do you verify? You just plug in and check like we've been doing so far this summer. We can also have an initial value on such a problem. An initial value can be given in the form y0 equals alpha. Basically, you specify the first term of the sequence, and then you build the rest of it just up from having this relation to get you the next term in the sequence. So those are some basic definitions for finite difference equations. They're very, very similar to those you would have for differential equations, but we just have them slightly different formulation because we have a different set of a derivative. Now, for the rest of this section, we're going to look at what are called autonomous finite difference equations. So similar to autonomous ODEs, where it meant the right-hand side doesn't depend on t, here it means the right-hand side doesn't depend on n. So I have, for these equations, no dependence on n on the right-hand side, just the dependence on the previous state. So how do solving these equations work? Well, if I'm given y0, then what is y1? Then y1 is just f of y0. What is y2? Y2 is just f of y1, which is just f of y0. So all we're doing here is just iterating the function f over and over and over again, and that gives us our entire set of values in our solution here. So when we have a system like this, there are two main things we want to look at when sort of trying to analyze what's going on. We want to look at the long-term behavior and equilibrium solutions. So by long-term behavior, I mean what happens as n goes to infinity. So if I keep iterating this over and over again, what's happening to my values? So long-term behavior just says, as n goes to infinity, what does yn do? And then equilibrium solutions because I want to know what I have for fixed values. So when is yn the same for all n, which comes down to when is yn equal to f of yn, or what is a fixed point of f. So there's the two things you want to look for when you're trying to analyze these finite difference equations. So the first thing the book does from here is they do an example of the linear equation, which is just multiplying by a constant every time. So we'll look at that real briefly at the beginning of the next video and then go on to the example we actually care about, which is the logistic difference equation. So basically we're taking logistic equation from section 2.5 and we're going to try to do the same thing here with a finite difference scheme instead of using the normal differential equation we had from before. All right, so that's it for this video. Thanks for watching this one, and in the next one we'll go into those two examples of difference equations.